Hello guys, welcome back. And now today we're gonna go through the 2023 Aime Ii problem 8. Let omega be equal to cosine of 2 pi over 7 plus I times sine of 2 pi over 7, where I is equal to the square root of -1. Find the value of the product, this monstrous product, which, as you know, that this is the other version of pi, which basically just takes the product from k equals to 0 to 6 of this expression, which omega is basically this monster right over here. Okay, so do we know what is cosine of 2 pi over 7? Well, we know that 2 pi in degrees is equal to 360 degrees. And 300 over 60 over 7? What is that? We don't really know, right? We don't really know what this value is. It's not going to even be an integer, and it's not that easy to deal with compared to, like, let's say 60 degrees or 120 or 45. So how are we gonna even know the value of omega if we don't even know the imaginary part and the real part? Now, if you guys have checked the video that I made before, I think it was 2022 AMC 12B number 24, I've covered some basics of roots of unity, and that was a pretty long video, so just try to check it out entirely. But omega, if it's written as this form, then this basically tells us that omega to the 7 is equal to 1. And this is one of the roots of this equation. And I'm just gonna briefly walk you through why is that. So we draw the complex plane, right? And this is I, and this is real number. Then, well, what is going to be cosine of 2 pi over 7, right? Since we know that every complex number in the real imaginary plane is going to have some kind of value in real number and some kind of value in complex number. So let's say if it's 3 plus 4i, for instance, then, and here should be an arrow, then we know that we're going to get 3 in the real plane and 4 in the imaginary point. Then therefore this would be our complex number. So now, what is even cosine of 2 pi over 7 plus I times sine of 2 pi over 7? Oh, we don't really need to care about what's value is going to be. We just need to know that it's just some kind of ordered pair, that this value is cosine of 2 pi over 7, and this value is sine of 2 pi over 7. And we don't really need to care about what their specific values are. So from here, the complex number should be like this. Now, looking at their complex and real plane, does that ring a bell possibly? Well, yeah. We know from the famous identity, which is sine square of x plus cosine square of x is equal to 1. And we also know that a modulo of, let's say, some kind of complex number called z, that's equal to the square root of its real number, the real part of z square, plus the imaginary part of z square. So let's just take an example of 3 plus 4i. Then its modulo would just be, or its magnitude is just going to be the square root of 3 squared plus the square root of 4 squared, the square root of 3 squared plus 4 squared, which is going to be 5. And this is basically just the distance from this point to the origin. So that's pretty straightforward. So therefore, we know from this that this one will be 1. So that is why this has this magnitude, that omega to the 7th is equal to 1. Well, because if you draw all of these, like all of the other values, like cosine of 4 pi over 7, cosine of 6 pi over 7, all the way to cosine of 12 pi over 7, then you notice that, and then all the way to cosine of 0, then you notice that this actually precisely forms a circle. That's why it's called, well, a bad drawing, excuse me, but that's why it's called a unit circle, right? So therefore that is basically why this is a root of omega to 7 is equal to 1. So now how is this gonna even help us solve this problem? Well, we don't really know what is omega to the 3k plus omega to the k, right? We only know that omega to the 7 minus 1 is equal to 0. That's all we know. So how are we gonna solve this? And you probably don't want to just list everything out, because you see that, well, there are 3 terms for every such omega to 3k plus omega to k plus 1, and there are a total of 7 identical or similar things that we have to multiply together, and that would give us 3 to the 7 equals to 2187 possible terms that we have to combine, and that is probably not a good idea, even though you might have a lot of energy on the actual Aime Ii problem. So how are we gonna do it? Well, since we know that omega to the 7 is equal to 1, right, then we probably want to try to make or try to create as many as powers of 7 on the exponents. So, like, let's say if I have omega to the 3 times 2, or let's just say omega to 3 times 1 plus omega to the 1 plus 1. Then what can we multiply, or what can we combine such that this multiple would have a lot of multiples of 7 on the exponents? Well, as you would expect it, you probably want to multiply 3 times 7 minus 1 plus omega to 7 minus 1 plus 1, right? And let's just try to multiply this out. This is omega to the 3 plus omega plus 1 times omega to the 18 plus omega to the 6 plus 1. That's equal to omega to 21 plus omega to the 19 plus omega to the 18 plus omega to the 9 plus omega to the 7 plus omega to the 6 plus omega cubed plus omega plus 1. Now this one can be simply written as omega to the 7 cubed, which is just 1. So 1, and this one is also 1, and this one's also 1. No, this one's not 1, and this one's also 1. Well, there's a 1 at the end, so that's definitely a 1. What about every other terms? Right, notice that, let's just say omega to the 19. We can write as omega to the 12 times omega to the 7, and I'm not gonna dive into the proof too deep here, but you can just do some kind of multiplication and use some exponent property, and in this one we already know it's 1, so therefore omega to the 19 is equal to omega to the 12. Now can we just do it again? Well, yeah, we can just write as omega to the 5 times omega to the 7, well, because 7 plus 5 is 12, and that's equal to omega 5. So that is how we're gonna reduce it. So essentially we can just see that any exponent would be eventually reduced to an exponent that is actually the modulo of it that was divided by 7. So what is 19 mod 7? Well, 19 mod 7 is gonna be 5. And, well, let's just write it somewhere here. It's gonna be 5. And 18 mod 7 is equal to 4. And 9 mod 7 is equal to 2. And 7 mod 7, well, we already know it's 0. And 6 mod 7, we know it's 6. We can't really reduce it. And 3 is 3, and 1 is 1. So notice that 5, 4, 2, 6, 3, and 1 are actually all positive integers that are less than 7. So we can just rewrite this entire thing as 3 plus omega plus omega squared plus omega cubed plus omega fourth plus omega 5 to the 5th plus omega to the 6th. Okay, so now can we possibly relate this with omega to the 7 minus 1 is equal to 0? Well, think about this. We can rewrite this as 2 plus 1 plus omega squared plus omega cubed plus omega to the 4th plus omega to the 5th plus omega to the 6th, since that is how we found it. And what is this? Does this kind of ring a bell? Well, yeah. If you had replaced W with like something else, with some kind of numbers, then you will just immediately spot it. It's gonna be a geometric series, right? You take W, you take omega to reach the next one, you multiply by omega once again, and all the way. You just keeps on multiplying by omega, right? So that's just simply a geometric series. And we know that for any geometric series, the formula is going to be a1 times 1 minus r to the nth over 1 minus r. Right? And plug in everything, right? A sub 1 is equal to 1 times 1 minus r to the n over 1 minus r. And here we basically have r is equal to omega instead. So 1 minus omega to the 7th over 1 minus omega. Well, actually, this one should be n plus 1, excuse me. So 1 minus omega to the 7th over 1 minus omega. And this becomes omega to the 7 minus 1 over omega minus 1. And now, does that kind of ring a bell here? So this sum is equal to omega to the 7 minus 1 over omega minus 1. Which is what? Which is just 0. Right? Since this part is 0. So therefore our entire thing just becomes 2 plus 0. Which is 2. So can we probably generalize, since we only have 1 and we need 3 more cases. But if we can just set, well, let's just say, set it to be omega to the 3, r plus omega to the r plus 1. Then we pair with omega to the 3 times 7 minus r plus omega to the 7 minus r plus 1. And we multiply this out. What's going to happen? So it's going to be, make sure to not mess up calculation here, 3r plus 3 times 7 minus r plus omega to the r plus 21 minus 3r. I'm just going to write it as 21 minus 3r. Then plus omega to 21 minus 3r. And then we plus omega to the 2r plus 7. And then plus plus omega to the 7 plus omega to the 7 minus r. Then we plus, well, at the end, omega to 3 times 7 minus r, and then plus, well, actually no, omega to the 3r, then plus omega to the r plus 1. So we get this at the end, and this one we know is 1, this one we know is 1, and this one we know is obviously 1, so we have 6 left, which is precisely being 21 minus 2r and 21 minus 3r and 2r plus 7 minus r, 3r and r. So as we expected from our experiment, then they must have some kind of a bijection relationship to the group of modulo 7. Well, actually technically not the group of modulo 7, since we have to ignore 0 here, so we can just simply include 0 here, and that's going to correspond. So we have a bijection. We have a bijection to Z27. So now let's just kind of reduce this a little bit, right? Well, we know that a multiple of 7 plus something mod 7 is just equal to the something mod 7. We can just ignore this. So negative 2r, which is 5r. And negative 3r is just going to be 4r. And 2r plus 7 is just 2r. 7 minus r is 6r. 3r and r. So notice we have 1r, 2r, 3r, 4r, 5r, and 6r. And if you have done like some kind of group theory or or some kind of more advanced number theory, then you know that these are in fact a bijection to the module of 7, or technically including 0. So then we can just conclude that if we just pair any of these in this form, then we're gonna get into 2. And how many ways can we combine? Well, we're taking from 0 to 6, so we can combine 1 with 6, 2 with 5, and 3 with 4. So we're gonna get 3 factors of 2. But don't forget about the 0, so we need to multiply this by omega to 3 times 0 plus omega to the 0 plus 1, which all the 3 terms are 1, so we have to multiply by a 3 in the front. And that is just simply our answer of 24 at the end. Thank you for watching, hope you enjoyed, and I will see you in the next video. Peace out.